Welcome to the Math 1, Unit 8, Lesson 7, Summary Video, Next Year's Gig. This lesson is a Solidify Understanding task, which takes concepts developed previously and helps you formalize those ideas. The purpose of this lesson is to make connections between standard and factored forms of quadratic equations and continue to interpret the key features of quadratic functions in context. One reality of the North Carolina State Fair is that planning for next year begins before this year's fair is over. Fair officials have already started looking at new bands to entertain next year's fairgoers. Johnny Baldridge and the Piedmont Boys is one of the acts the North Carolina State Fair planners are considering for next year's fair. At a recent concert, 1,000 fans spent $20 per ticket. Market research suggests that for every dollar a ticket price goes up, 10 fewer people would come to the concert. The profit, J of x, from the concert can be modeled by the function below, where x represents the number of $1 increases in the price of the ticket. And so you can see the function written right here that represents this given situation. So the important information from the story. We know that 1,000 fans attended the last concert and they each spent $20 per ticket. We know that for every dollar the ticket price goes up, 10 fewer people attend the concert. We know that J of x represents the profit, and we know that the variable x represents the number of $1 increases in the price of a ticket. So these first two questions want us to describe what each of these linear factors represents in the context of the story. When we look at the first linear factor, we see 1,000 minus 10x. Well, we know that 1,000 represents the number of fans that attended the last concert. We know that the negative 10 is 10 fewer people that attend every time the price of the ticket increases by $1, and the price of the ticket increasing by $1 is represented by x. So for every time we raise the ticket price $1, we're going to subtract 10. So we're going to be repeatedly subtracting 10 every time we raise the ticket price by $1. That's our x. So the minus 10x, this term represents how many fewer people are attending the concert from the original 1,000 people based on how many times we've raised the ticket price, $1. So altogether, this linear factor represents the new number of people that they would expect to attend the concert based on how many times they've raised the ticket price. The second linear factor is 20 plus x. We know that 20 is the original cost of the ticket, and x represents each $1 increase. So altogether, this factor right here would represent the new cost of the ticket price. Number 3 says J of 0 means they have not increased or decreased the price per ticket, meaning there have been zero $1 changes. What would the profit be if they kept the ticket price at exactly $20 per ticket? So instead of the function being set equal to J of x, we're going to set it equal to J of 0, and wherever we see an x, we're going to substitute in 0. Then we're going to simplify, and we find that J of 0 is equal to 20,000. And so that represents a $20,000 profit or income if they don't increase or decrease the ticket price at all. So if they continue to sell the tickets for $20 a piece, they would make a $20,000 profit, and they would have 1,000 people attending. And you can see the 1,000 is still there times the $20 per ticket. And so then the next question asks us, well, what would J of 30 mean in context? And what would the profit be if they changed their ticket price in that way? So we know that X represents the number of $1 increases. And so J of 30, or X equaling 30, is saying that we have now increased the ticket price by $30, which means that the new ticket price would be $50. And so we're going to use the same strategy as the last problem, and we're going to substitute in 30 for our X variables, and we're going to simplify, and we find that J of 30 is equal to 35,000. And so what this means, again, is that we would have a $35,000 profit if we sold the tickets for $50 a piece. $50 a piece is what we get when we have the original $20 ticket price, but we increase that by 30 $1 increments, or by $30. This 700 represents the 700 people that would be attending, because remember, 10 less people are going to show up every time we increase the ticket price by $1, which means if we increase it by $30, 300 less people are going to show up. Therefore, we'd have a total of 700 people that would be attending altogether if the tickets cost $50 a piece. Again, we would have a $35,000 profit. Number 6 asks us to type the function into a graphing calculator using the profits and $1 adjustments above to help you determine an approximate window. If J of X equals 0, find the solutions for X. What do these solutions mean in context, and where are they on the graph of the function? So we're going to look at the graph through Desmos first, and then we will look at finding the values or the solutions for X after we finish going through this with Desmos. So using Desmos, I went ahead and typed in the function that we were given in the problem, and notice that I was able to type it in factored form. And when I click on this button right here, it will go ahead and display the graph. Now I can click and hold this button, and I have the option of changing the style of line, or dotted line, or partially segmented line. I can also change the color, and so I'm just going to leave it as a full function there. And if I click on the wrench over in the top right hand corner, I can adjust my x-axis, so what will display on the screen, and then I can also set the parameters for my y-axis. I can add labels here if I'd like. I can adjust my intervals, and then I can use these zoom in and out buttons to help me. I can also do that with my mouse. And so I'm going to click in here. I'm going to edit this list and duplicate this. And then from the duplicated function, I'm going to convert the function to a table. And so it went ahead and did that, and it put in these 5 x values, and you can see how those were plotted there on the function. Well, that's not super helpful for me because they are just in a cluster right here. What I can see is that my x-intercepts are -20, 0, and 100, 0. And so I'm going to start my table at -20, and I'm going to go in increments of 10. Goodness. And then I can just hit enter. It picks up the pattern for me. And so I can easily see my x-intercepts here. I can see my intervals of increase. So it's increasing all the way up to x, from x is -20 to x is 40. And then the intervals of decrease are from 40 to 100. I can see that my vertex is at 40, 36,000, and that would the 36,000 would represent the maximum profit that can be obtained through this concert. Because remember, my Y values represent the profit, my X values do not represent the ticket price. They represent the number of $1 increases to the ticket price. So this 40 is not the price per ticket in order to result in a profit of 36,000. The 40 is how many times we've raised the original ticket price of $20, and we've raised it 40 times, which means that the ticket prices would need to be $60 in order to have a maximum profit of $36,000. Likewise, this point represents zero profit, as does this x-intercept. They both represent zero profit, and this is saying I have reduced the original ticket price of $20 by $20 or by $21 increments, meaning that the ticket prices are now zero or free. And so we know that if we don't charge anything for the tickets, we're not going to make a profit. And if we were to go less than, say, to -21, we would actually be giving each attendee $1 to attend, which would result in a negative profit. So that's when we're going below this x-axis. Over here at the other x-intercept at 100.0, it's saying that the ticket price would actually be $120. It's saying that we're taking the original ticket price of $20 and we're raising that 100 times by $1 each, or by a total of $100. So anything, if we sell the tickets for anything between $1 and $119, we'll make a profit. And we're going to take a look at this also using the TI-84 Plus calculator. So if we push this button right here, the Y equals button, that's where we can enter in our function. And again, we can enter this in factored form. And if you were to, well, let's do this first. So if we press the window button, this allows us, just like in Desmos, we were able to click in the top right-hand corner of Desmos to adjust our intervals and our parameters for our X and Y intercept. We can do the same thing by pressing this window button. So we can set the minimum and the maximum for our X-axis and our intervals, counting by tens. We can set the minimum and maximum for our Y-axis, and using intervals of 1,000 because we're going all the way up to 40,000. And these are things that you'll just have to kind of use your best guess to figure out how, just like when you're graphing by hand, you need to kind of determine before you start graphing what the range needs to be for your X and your Y axis, and then determine the intervals. Well, it's the same thing when we're either using the graphing calculator or Desmos. We need to figure that out as well. Otherwise, our graph may not show up on our screen. So if I go back to the Y equals, I can see my function is still there. And if I now hit this graph button, I can see the graph on my screen. And I can, this blue calc button, I can press that. So if I want to access anything in blue, I need to push the second button first, and then I hit trace. And so I can find my zeros, which are my x-intercepts. And you'll notice when I push that, it says left bound, and I have this blinking cursor. And so I'm going to hold this down, and it's going to keep blinking, and I'm going to go below my x-axis for the left x-intercept. And then I'm going to press enter, and then it says right bound, and so I just need that to be above the x-intercept. And so I'll hit enter, and then I'll hit enter again for guess, and it tells me down here that my 0, or my x-intercept, is located at -20, 0. And I can do the same thing for my other x-intercept. So I'm going to scroll this all the way around, and I need the left bound to be to the left of the intercept that I'm looking for. So right there is fine. And then I need this line to be to the right of it, or not really the line, but the little cursor that I just moved. And so it's down below or to the right of it. And so I hit enter, and then I hit enter again, and it tells me that my other 0 is at 100, 0. I can do the same thing to find my maximum, which is 4. And so again, it says left bound, so I need it to be to the left of the vertex. And I'll push enter, and then I will scroll it to the right of the vertex. It says right bound down here, and I'll press enter, and then it says guess, and I press enter again, and it tells me that my maximum, which is my vertex, is located at 40,36,000. And so you can see how we can find the same information using our graphing calculator as we can with Desmos. And you can convert this graph to a table, and there's lots of different functions that you have all the same access to information regardless of which method you use, which piece of technology you use. And there are tons and tons of tutorial videos located on the internet if there's anything that you want to know how to do. And so going back to number 6 in your booklet, it asks you again to use your graphing calculator or Desmos to look at the graph, and then it asks you to find the solutions for x for the function when x is 0. And so we can see how we start with the original factored form of the function. We use the zero product property to set each linear factor equal to 0, and then we solve for x. And so what we see is that x equals 100 and x equals -20, and we saw those on our graphs as our x-intercepts. And just like we talked about in the previous video, the solutions to the quadratic function are the x-intercepts. They represent the x-intercepts. And finally, we're going to look at problem number 8. It says write the function for Johnny Baldridge and the Piedmont Boys in standard form, and what information can we easily gather from the standard form of this function. And so we know that in order to convert the factored form to standard form, we've got to use the distributive property. So we are distributing that first term in the first factor to each of the terms in the second factor, and the second term in the first factor to each of the terms in the second factor. And then we will simplify by combining like terms. And I reordered so that it's going from, we have our terms with our variables first, and starting with the highest power. And from the standard form of the equation, we have this 20,000. And if you recall, our y-intercept when we looked at the graphs was 0, 20,000. And so what that was saying was that if we charged $20 per ticket, or if x was 0, if we did not have any $1 increases or decreases, we sold each ticket for $20, we would make a profit of $20,000. So from the standard form, it tells us our y-intercept, and from the factored form, which we looked at just before this slide, we are able to see our x-intercepts.